In this video, we are going to do a practice problem involving finding a line integral of a vector field. So the question says, given this vector field f, I want to evaluate the line integral of the vector field, where C is given, our curve is given by this parameterized equation. So, I first want to just recall, what does this notation mean? How do I evaluate it? This line integral, when I have a line integral over my curve of f, and then dot that unit tangent vector t hat ds, this becomes an integral over my interval for t, which is from 0 to 1, and then I have to substitute in my parameterization into my vector field. So I would write that as f of, and I got to sub in the parameterization, r of t. Okay, and the unit tangent vector, and I have dot unit tangent vector, remember, it is the velocity divided by its length. That's the unit tangent vector. And then ds is the length of velocity dt. So our unit tangent vector is this, and then the ds is this. And as we've seen before a number of times now, the length of velocity here and up here, they cancel. So we'd get the integral from 0 to 1 of our vector field f of r of t dotted with the velocity dt. So if I wanted to work it out directly, we'd get this type of thing. So I want to have you now pause the video for about 5 minutes to try this. Pause in 3, 2, 1, pause it and try it. One of the big things you'll have to think about is, should I tackle this directly? Is there another way to approach it that might be more helpful? Okay, so hopefully you paused it to try it. Let us think about it now. Let's talk about it. So if I were to do it this way, I would now need to figure out f of r of t. So, okay, f of r of t means take this parameterization, so I have this x component, this y component, plug those into my vector field. So wherever I see an x, I'm going to plug in what x is from the parameterization into here and into that x. And now I'm going to plug in y in where I see the y here. Okay, so if I do that, I would get a vector that has 2 times this x component, which is t cosine of pi t minus 1 times y. Y is this big old thing in parentheses. I'm just going to put a squiggly line here, and then comma, and then I'd have whatever the y component is when I plug in for that. Because I already noticed that this looks so complicated. This is very complicated looking. So I'm from a sad face. I'm really, really hoping that there's a better way to do this. And luckily there is, which is to try our fundamental theorem of line integrals. And I'll abbreviate line int. Okay, so remember the idea with that is we try to find a function lowercase f such that the gradient of little f equals our vector field. Okay, so what I need then is we need the partial derivative of f with respect to x to be equal to this x component, 2xy. And okay, let's start with that. Now let's do the antiderivative. So I'm going to do the antiderivative with respect to x, meaning I'm treating x as a variable and the y gets treated as a constant. So the antiderivative of 2x would be x squared. So I'd get f equals x squared. And y is just a constant multiplying that, so that stays there. And then normally when I do an antiderivative, I get a plus c, but we're also treating y as a constant here. So not only will I get c's in my constant, I may also have y's. So generally, to this, I need to add some function of y, which I'll call c1 of y. And I could check that now when I take this f and I do its partial with respect to x. For this part, that partial becomes 2xy. For that next part, I'm treating y as a constant, so that partial is 0. And then adding those together, I do get this, which is good. So now let's match up the y components. So when I take this f and I take its partial derivative with respect to y, the x gets treated as a constant, so that x squared stays there, multiplies the derivative of y, which is 1, okay, and then plus. This next portion is just, in terms of y, just one variable. So instead of doing a partial of this, I can just do a normal derivative, which would be c1 prime of y. So that whole thing needs to be equal to this y component. So that y component is x squared plus 1, the y component of f. Okay, so matching these up, I can subtract x squared from both sides, and I'll get c1 prime of y equals 1. And now I can do an antiderivative of that, so I'll put an arrow. So the original function c1 of y, there's just one variable in here, so this is a normal antiderivative. Antiderivative 1 would just be y, and then I need plus a constant. And now it's just c, it's not a function because there's only one variable here. Okay, so now I know what c1 of y is. It is y plus c, and I will plug that back into f. So my function f, and I'll write it as f of x comma y equals x squared y plus c. And then I can use my initial point and my ending point, which is based on what t starts off as. It starts off at 0 and t ends at 1. And we plug those into the parameterization. I'm going to trust that, that we can do that, and I'll just tell you what you end up getting. If you plug in 0, you'll get the point -1 for x, 2 for y. If you plug in 1, you'll get -2 for x and 3 for y. So now by our fundamental theorem, we will end up getting our function, lowercase f, evaluated at that ending point, -2 comma 3, minus our function f evaluated at the starting point, -1 comma 2. So let's plug these in. So if I plug in -2 comma 3 in for the x and the y respectively, I'll get 4 times 3, which is 12, plus y, which is 3, and then plus c, and then minus, plug in a -1 for x, 2 for y. This first term becomes 2, and then plus y, so plus 2, and then the other plus c. So subtracting these, I'll get 15 minus 4, which is 11, and the c's cancel. So overall, I get 11, and that's my answer. So overall, in terms of our goals for this section, we have now practiced our last goal through some examples, recognizing when and how we can apply this fundamental theorem of line integrals. And in this example, we saw one of the situations that indicates we may want to try it is if our function is very complicated to work with otherwise. It's an indicator to try using this.